are continuing in the 6-3 notes.
Hi.
Let's go, people. 6-3 notes. Oh, okay.
6-3 notes. Thought we finished those.
I don't think we're
We're
gonna
not gonna finish these.
There's a lot of like application problems that kind of take a while. All right, so as students are getting their notes out, I'm just gonna refresh. Yesterday we learned this new linear combination form, and it's basically just another notation or another way to represent a vector. So, in summary, these three vectors written in three different forms as a direct line segment, component form, linear combination form, all represent the same thing, just written in different notations. So we practiced one problem in the linear combination form, and really you just take your horizontal component first, tack on an I, which is our standard unit vector, vertical component second, tag on a J, vertical component. Okay.
You sure you want to do this? There's a lot of people doing it.
Yes, I'm sure. So basically all of the same operations with vectors apply in this form as well. Okay, so we went through and said, how do you add two vectors together? You just add their matching component parts together. Same with like linear combination form. So if I wanted to have this scalar 2 times my vector v, so you can see here my vectors are written in that linear combination form. I have a vector u and a vector v here. So if I wanted to find 2 times that, I'm just going to double each component part. So you can almost set it up like this and distribute the 2, but you're just doubling the horizontal component. Make sure you're not italicizing your I. Remember that means imaginary number. And then you're doubling your vertical component. If the original vector is given in linear combination form, you want your resultant vector to be in linear combination form. So don't write that in component form. If you want to, you could like convert it to component form and then convert it back, but that would just be extra work, where really it's just all the same operations apply. Okay, let's try a little harder one. If I have 2 times my vector u minus 3 times my vector v, so I would start by doubling my vector u, and again, I'm just going to keep it in that linear combination form. And then minus 3 times my vector v. Okay, so let's go ahead and distribute. Let's do the scalar multiplication first. So negative 6i, just like you would do if this is like a normal like algebraic expression. Minus 6. Oh, I almost did the cursive I. Plus 3j. And then we know if we want to add or subtract, for that matter, vectors, 2 different vectors, we just add their component parts together. So their horizontal components would be negative 12. Vertical components, 19. And we looked at yesterday what this looks like visually, how we could like stack the vectors on top of each other, how we could double them, how we could subtract them, all that good stuff. So if you were to graph these, because you're given the component forms, and do it geometrically, you'd get like this same resultant that we looked at yesterday. Okay. That's all we need to do with that. Basically, all the same rules apply in this new form. All right. Next thing we got to talk about with vectors, which this kind of relates back to some of the trig stuff we've done.
Yay. I'm happy.
No.
With vectors, so we talked about how vectors represent like magnitude and direction. So another way we can describe their direction is by angles. Okay, so we have something called their direction angles, and similarly to like when we did like the unit circle, the direction angle is the angles that it makes with the positive part of the x-axis. Okay, so it's kind of like where we would always, when we started just like graphing angles in standard position, how we would start the initial side here and like rotate the terminal side. So we measure the direction of the angle with the angle that it makes with the positive side of the x-axis. Okay, so there's not like two rays here. Like this is still my vector, and then this is the angle we're talking about when we're talking about the direction angle. Okay, so let's just look at something on the unit circle, pretty basic here, that lies in quadrant 1. So do you guys agree that for this vector, u here, the horizontal component would be the cosine of theta? And we talked about that before, why x represents cosine when we did all like the unit circle stuff. But because, you know, this is x. This direction is obviously what you're plotting, like your x coordinates, cosine of that angle, yada yada. Okay, we don't need to go through all that again. And then my vertical component would be like the y coordinate of where this intersects, or whatever the sine of theta is. Okay, that's component form. In linear combination form, we could also say that this would be the same as the cosine of theta, horizontal component I plus sine of theta is my vertical component j. So the little like formula you really need to know if you want to use the direction angle to help you like find out stuff about your vector, like it might ask you like, here's a direction angle, find the magnitude, or like here's the magnitude of the vector, find the direction angle. Here's a little like formula you need to know, and it kind of comes from this visual here. That any vector, and I'm just going to say v, basically that's like not on the unit circle, so that doesn't have like a magnitude of 1. Anything that doesn't have a magnitude of 1, we can take the magnitude to figure out like its component form, and then times the cosine of theta and times the sine of theta. So basically you're like factoring in the size of that vector here. So if you're given information about the direction angle, this is how we can figure out what the horizontal and vertical components are. Okay, I like to visualize it. I'll often draw, we'll do it with numbers in a second, but I like to like draw the vector and then like make my little right triangle, just like we did with reference angles and stuff like that. And then I can visualize, oh yeah, here's my right triangle. Here's my angle, so that'd be the cosine of that angle, would give me my horizontal component, and then you just have to factor in like the size of that vector, aka like the hypotenuse of that little right triangle. Okay, so this formula you'll be using a lot, and it's basically just like I said, used in many different applications if you were given the component form and you need to find the direction angle, or vice versa. Maybe you have to find the component form. So I'll walk you through a couple examples. Here's like a pretty classic one where you're given the linear combination form of the vector and you need to find the direction angle. Okay, so I personally like to see this in like component form. You don't have to, but for me it's like kind of easier to graph the vector if I see it like written in that component form. So this vector u just says we have a horizontal component of 3 and a vertical component of also 3. So what quadrant is my vector going to be in?
1.
1, right? I have a horizontal component of 3. You don't have to be super accurate until we start doing application problems.
Yeah.
And remember, in that component form, initial point is where?
0, origin.
Origin, good. And then that'd be my terminal point. So there's my vector. They want me to find the direction angle. So remember, it's the angle from the vector to the positive side of the x-axis. So this right here. So this is what I was saying. I personally just like to draw this, make it a right triangle. I know this horizontal component is 3. I know this vertical component is 3. Using right triangle trig, how could I find theta? Pi theta would give me the magnitude of the vector. if I wanted to find that, I could use Pythag. How would I actually figure out the angle? Tangent. I like that idea. Tangent of theta. Tangent of theta is 3 over 3. Which is the same thing as 1. So guys, what would that angle be?
45.
45 degrees. Oh, another thing, a lot of the times our direction angles are measured in degrees. So we're going to write this as 45
If
degrees.
you not have told that because it's a special triangle, it's a 45, 45, 90 triangle.
You could have, yeah. You could have done it that way too. Oh my gosh, we're learning those today in geometry. 45, 45, 90s, and 30, 69s. I'm so excited. And then when I come back on Monday, we're going to do SOHCAHTOA. So many exciting things going on in my life.
Yeah, my prayer.
Can I go back in time?
Where are you going?
She's not coming back.
A wedding.
I'm going to get hitched.
What's that mean?
Get married. It's just
My
hick,
gosh.
hick way of saying it.
Gonna get something, I guess.
I'm gonna tell my mom you said that.
Fired.
Okay.
Since you're just talking about getting hitched in class.
Don't worry, it's going up on
You
YouTube. I'm
join
recording
Judy on the
this.
Fryers.
Okay, that hopefully the mic didn't pick up. All right, let's try another one that's not so easy. That's not a 45, 45, 90 triangle. All right.
Yeah, that one was for math.
That one.
I better not put this on YouTube. I better just download it as a Google Drive link. All right. This time, vector B we have here, if I were to write this in component form, horizontal component of 3, vertical component of -4. What quadrant?
4.
4. Good. 3, -4. So go ahead and sketch in your vector. Okay, now, not to get confused with reference angles, we'll use that in a second. The direction angle of this vector is from the positive x-axis to the vector. So it's that big angle right there. That's my direction angle. I'm going to call it theta. Okay, that's how we measure direction angles. Now, I am going to use this little angle right here to form my right triangle, and I'm going to call it theta prime, aka my reference angle, because we can use this the same way when we did trigonometry stuff. And then I can use right triangle trig to figure out the reference angle, which will help me find the direction angle. So this is still 3. Technically, this this vertical component is -4. Could I still use tangent for this one? Yeah, the tangent of theta prime is opposite over adjacent. Okay, now this is one that's not on our unit circle.
Wow.
So how do we do it?
It's a shame my calculator's dead.
Trash up.
Inverse
And a
tangent.
-1.
Inverse tangent, good.
Inverse tan.
Trash up.
All right, now make sure your calculator for this is in degree mode.
You sure you want degree mode?
Yes.
Positive.
In your calculator is going to tell you this.
User error.
Love that.
I got a negative angle.
Okay.
Make it positive.
Oh, okay.
But this is when we can't just rely on our calculators. We got to be smarter than our calculators. We know for inverse tangent,
Take 360.
we're only defined from -90 to 90. Okay? So there's a couple ways you could calculate this. Yeah, we know this angle would be like 360 minus out that little angle, or you could just take 360 plus that. Your calculator is going to give you that answer because it's calculating this angle right here, which technically that is a negative angle in that direction.
Mm-hmm.
Makes sense? But obviously, like, however you want to think of it, that angle right there is like 53 degrees about. Technically not a negative. So to figure out the actual direction angle, I just did 360 plus that. Or think of it as 360 minus that angle. That's the actual direction angle. So I got about 306.8698 yada degrees.
Man, I really thought we were going to be done with this whole music.
Oh no.
I'll be with you forever.
Okay, we're gonna try a couple different examples where One of them I like give you the direction angle, and you're gonna have to find the vector. And then another kind of like vector one using direction angles, but let's try this one first. Given, what's this?
A crop.
The magnitude. Given the magnitude is 5 of this vector v, and the vector has a direction angle of 30 degrees, find the vector in component form. Now, you can sketch a picture, and if you want to, you can to get a visual. But here's where we're going to use that little like formula I showed you. Is I know that the horizontal component is just going to be the cosine of whatever the direction angle is, and they give us the direction angle. I know the vertical component is going to be the sine of whatever that angle is, and then I just have to factor in the length, aka the magnitude of the vector, and then I can get what the vector is in component form. Okay, I'll draw it out too in a second, but all you need to know is, hey, we could find that vector v, and this formula you want to have memorized because this comes in handy in a lot of different types of problems. I can take the magnitude times the horizontal component and the vertical component by factoring in like the direction angle. So if I were to sketch this, direction angle 30 degrees, and I know the length of this is 5. Right here. I know this is 30 degrees. So yes, you could draw a picture and you could do trig if you want to. But we know the magnitude is 5. So we're just going to take the cosine of 30 degrees and the sine of 30 degrees. And then we're just going to times them all by 5. Okay, when you can use exact, we want to. So these ones are on a unit circle. Do you guys remember what the cosine of 30 degrees is?
Square root 2.
Square root 3/2.
I knew that. I just didn't want to say it.
Didn't know it.
Sine of 30?
1/2.
1/2.
You did use the unit circle.
Yes.
No. Alright.
I don't know. I'll think
We
about it.
already got tested on it, so we already know.
Yeah, so we should know it.
Well, apparently you don't, because I just asked
You don't.
what the cosine of 30 is and 2 people do.
Well, yeah,
I
those
just
two.
do
Wait,
think of it
if I
in
sketch it
one.
out,
Yeah, I
can-
100% kind of do.
I believe you. That's 100%.
Okay, so there's that vector in component form.
You circled red.
No, I would have known.
I don't
Just
know,
have to
something
give me a
fun.
few
Fair
minutes.
enough.
I'm slow
I did too.
with the unit circle.
So guys, obviously, like, so this is the horizontal component. That's this distance. You could have also like just called this x. You could have solved this using right triangle trig.
Yeah, that's what I was saying.
You could have, that's fine. You could call this y. Some of the word problems, it's easier to do it geometrically than like, I call this analytically, like doing like the algebra kind of.
Trash.
Sometimes it's easier to set it up and like visualize it. Don't worry, when we do some application problems, I'll show you both ways. And then you can decide.
Oh, yay.
You can be the pilot of your career.
Sounds fun.
Okay,
Yay.
either way, obviously, x, we take the cosine of that, which is x over 5, and then that factors in like the magnitude. Okay, let's try another one. This one's kind of a fun problem. Fun little problem.
Looks amazing.
Find vector v if it has the same direction as vector u, which in component form is 2, -5, and we're given that the magnitude of vector v is 4. Okay, so the same direction as vector u, so let's figure out where vector u is. 2, -5 would be, again, quadrant 4. Okay. So we don't know that it's located in the same position, but we know it has this like same direction, so like the same slope. So what we'll have to find is we're gonna find the direction angle. And then that direction angle should be the same for vector v. So we can use that, and we're given the magnitudes, and then we can write it in component form with that little formula. Okay, so let's use this reference angle right here. Let's draw a right triangle. All right, we know this is 2. We know this is -5. Okay. So you could like go through and like actually figure out like numerically what the angle is, but we don't really need to here. We know that in order to find the component form of the vector, all we need to do is find the magnitude times the cosine of the direction angle times the sine of the direction angle. So we can just use our picture here to find like the cosine of theta using the right triangle. And we can do this without actually finding the numerical value of the angle. We did problems like this a lot when we did like the identity problems where you're like, hey, given that the ratio for secant is this, find half of these angles. And we did that with just using the formulas, drawing a picture, and not actually calculating the angle, if you kind of remember that. I'm going to go ahead before I use that. I'm going to plug in. I know my magnitude for vector v is 4, so I know that. Okay, so the cosine of theta. So looking here, and I'm using theta prime as my reference angle, and that's fine. Again, I know this is the direction angle, but as long as it has the same reference angle, we're good. Would be adjacent over hypotenuse. Oh shoot, I don't know what my hypotenuse is. How could I find that? Pythag. Okay, I'm telling you right now, it ends up being the square root of 29.
Wait.
Yep.
Thanks.
It's not 4. That's the length of the vector.
How come it's not 4?
So that's the length for vector.
This is vector u. This is vector u.
Oh, yeah.
Good call. I'm going to label that. This is vector u. I'm just using this direction because I know it has the same direction. All right.
But don't vectors have to be the same length?
I never said that these were equivalent vectors. We just know it has the same direction. But yes, in order for two vectors to be equivalent, they have to have the same magnitude. It doesn't say that. It just says find the vector v. It has the same direction as this
I
vector.
thought that they always have to be the same.
That's if they're equivalent vectors. That's not stated to us. All that's stated to us is that they have the same slope.
Yeah.
They're going in the same direction. Okay. And we're using direction angles to do that. Okay, so you can rationalize it from here, or you can wait to the end. I'll just go ahead and rationalize it. So the cosine of theta is 2 root 29 over 29. Sine of theta, sine of the direction angle. The only problem with getting the actual numerical value is when you go to like use your calculator to figure out what the sine and cosine are of that, they're not going to give you these exact answers. Okay, so you want to use your picture. Sine of that reference angle would be negative opposite over hypotenuse. So let's go ahead and rationalize that. Do you guys remember the first time you learned how to rationalize denominators? Do you remember what class you were in?
Algebra.
Algebra 1? Okay, because my geometry kids claimed they'd never done it before. And I was like, pretty sure you do it in Algebra 1, but... Okay, thank you. So then we just have to times this all by 4, factor in the magnitude, so you get 8 square root 29 over 29 negative 20 root 29 over 29. Okay, so there's that vector. That would have the same direction as this guy using the reference angle. It had the same direction. We factored that in, and it has a magnitude of 4 in component form. Not a very nice numbers.
Oh, those are beautiful.
That's what I thought.
What you talking about?
Oh, these are so fun. You guys are gonna love this.
Look at time.
What's not fun to you? I'm very curious.
Writing papers.
I can agree with that.
We suck at it. I'm so slow.
Well, that's what you do for being a math teacher, so.
Okay, so we're gonna start to get into application problems. Probably not today.
Law of cosines.
But-
again.
Eventually we will. And there's, as I mentioned, there's kind of like two ways you can solve it by like geometrically plotting the vectors and using like right triangle trig, or using law of cosines often helps us. Because once you kind of slide some vectors around, you can like form triangles. Okay, so I'll show you that in a second. Or we can solve it like algebraically by putting things in component form, adding them together if we need to find like resultant vectors, or finding like like using this formula. We can do it kind of like analytically, but this is kind of cool. So by subtracting two vectors, a third vector can be found which completes and forms a triangle. So let's picture this. Ooh, I can do this again. Let's do u minus r. So I'm going to take vector u. There's u plus vector r, so I'm going to minus it going in the other direction. Sometimes I just like to dash it. So go ahead and draw that in. Try to do it at the same steepness, same direction, and the same length.
Will do.
I know this isn't on a coordinate plane, but that's fine. Yeah. Oh no!
There goes another
Oh
one.
my gosh!
Oh,
doesn't-
you just broke that
Oh.
thing.
That's.
Ah, I'm down to 2.
Let me see it.
That thing
That's
is
so
not
funny.
like-
I just really
Wasn't your last
ruined a
red one
marker,
like this too?
and I'm missing my
Black
black
one.
marker, and now I'm missing the one. I'm so sorry. Those were really expensive.
They buy them in packs of 4.
Factor is a budget.
And this one sucks. This one, half the time I write, it erases. Like that.
I think Nate has some in his room.
I think
I should go ask. I'm too embarrassed to go in there because I've done it 15 times.
I'm working on the market.
at like
Yeah, I'm like,
$500.
Well, you see, the thing
oh,
is,
do you fix it?
I mean, I put it back together. It's not gonna work.
Sad day. Okay.
Rip the ribbon out of it.
Well, all right, people. Time. It's been real. All right. So then this vector right here would be what we call like our resultant vector. This would be, let's call it v. This would be u minus r. Okay, so you can see this triangle that's formed. So maybe let's go ahead. Oh my gosh. Let's just
Don't
drop
drop
another one. Did you
It's
see-
Hendrick.
I caught that one.
I
Did
think
you
we
see
need to
it?
call it that.
Is it just our
Oh,
class?
yeah.
No, it's all day. Every
you
day.
really need a budget for a map.
Oh my gosh. Let's actually go ahead, fill that in solid so you can see the triangle. Fill that in solid. Okay, so see how we have this little triangle that's formed?
Yep, it's
Yeah.
a beautiful
And
triangle.
it's not a right
I'm
triangle.
not crying.
I mean, it could be depending on what the angle between R and U is. But we know that these are going in the same like level of steepness, right? Can we visualize that? So these are like parallel to each other.
The same slope.
Same slope. Yep.
What is parallel?
Same slope. So would you guys agree?
Never understand. They will never, ever,
I
ever.
thought it was straight. Stop.
So would you guys agree that this angle right here, I'm just gonna call it theta. Sure, theta. This angle between R and U would be the same, picture U as like a transversal alternate interior angles as this angle right here. Okay. So usually if we know the magnitudes of these vectors, if we know the magnitudes of lengths, we can figure out this length. And then if we know 3 sides of a triangle, how do we solve for some angles?
Pythag.
Law of cosines. Only if it's a right triangle. But in Pythag is only for sides.
I thought that's what you said was 3 sides.
Why would you do Pythag if you know all 3 sides, right?
Find the 4.
I look at that green one.
I'll
Find
find
these
the
squares.
last section, how long that is.
Okay, so here's a little law of cosines refresher and reference to this. So let's say I want to find that angle. I would take this opposite side, which is my resultant vector, I'll say v. I would take the magnitude of that, and that's the same as this side, which is the magnitude of u, plus this side, which is just the magnitude, and that's length, so you don't need to think it's negative, it's just length. Okay, you guys remember law of cosines? Minus 2
No.
times the length of the 2 sides that include the angle.
Yeah.
I'm
How
drawing
many
a
times I've changed
bracelet.
my colors?
Times the cosine of theta.
Changed my color like 20
Oh,
times.
that's
That's
I'm still in the lines.
Gosh. Okay. So right, visually see that.
Yeah.
Why that?
Visually.
Why that would work?
I did just see it, but I don't mentally understand it.
Okay, let's do it. We'll do a practice round. Don't worry.
I mean, I don't understand it, but
They're all lines.
This angle would be the same as this angle because they're going in the same direction. You're gonna know, or you're gonna find the resultant vector either geometrically or using it algebra by putting it in component form. And then you can find any of the angles by using law of cosines because you know the three sides, you know the three magnitudes, and that's what that is. It's just law of cosines. Wait, these are squared. Sorry, these are squared. These are squared. These are squared.
Oh my.
Because that was law of cosines. They have to be squared.
Yep, they're squared. I forgot to put that in my notes.
We should super
Yeah,
these
I
before we
don't
get back to you.
I need to fix that. Okay, let's try one. So, these are given in linear combination. No worries. I'm gonna do, I don't know. I'm gonna write in component form just above it.
On the next one,
3, -2. V, I'll do in green. 2, 1. Use the law of cosines to find the angle between the vectors. All right, so let's go ahead and sketch this quick. So I'm going to try to be a little bit more accurate. There's vector u, vector v is 2, 1. Okay, so I want to find the angle between these two vectors.
74 degrees.
No.
You got to find magnitude.
Okay. First, before we find the magnitude, we do have to do that. First, let's figure out and form this a triangle. Wait, can we just do u minus v?
Oh, nice.
V minus u.
I see it.
No, we can't. All right. First, we gotta find. Oh, great! Now my marker's just not.
The color.
U minus v.
I'm using it every day.
We could do this by using our graph. We can also do this really easily from their component forms, right? So horizontal component of u3 minus v minus 2 would be 1. Vertical component -2 minus 1 would be -3.
right out.
Okay. So here's that resultant vector. I just called it u minus v.
Is that 1, 3?
It's 1, -3. And you could picture this by doing this. Oh man.
Oh.
Minus that. Okay, everybody see that?
Yep.
Okay, so I'm gonna go ahead and I'm gonna draw that negative or minusing off that vector v right here. So that's the opposite of vector v. And this is vector u. Right, u is my blue one. Yep, u. So then that black one I drew in is u minus v. Okay, so based off what we just talked about, this angle right here is going to be the same as this angle right here, alternate interior angles of those two parallel vectors. So we're going to find the magnitude of u, find the magnitude of v, find the magnitude of u minus v, and then use law of cosines to find that angle, which is the same as that angle. Are you guys ready for this?
Y'all ready for this?
No.
I'm not crying.
Are you crying?
No.
You use
Only
That
a
was
little
so-
bit.
Shut up.
Only on the inside.
He's a man. He can show up on the outside.
Okay. So
Argue.
in component form, do you guys remember how to find the magnitude? Just like by giving their components really quick and easy.
V1 squared plus V2 squared under the square root sign.
Good job, Carter. You just take their
I misspelled sign.
horizontal component squared, vertical component squared, and you square root it. You're really doing pi thing there. Okay? So you're taking the horizontal component squared plus the vertical component squared, and you're square rooting that to get the length of that.
Root 13.
Do that.
Nice.
Oh no.
Okay, there's magnitude of vector u. So same thing for vector v.
Why is it so big? I was losing 500%.
Bless you.
You're
So
welcome.
we're in. Picture over here.
Root 5.
Okay. Magnitude of u minus v. Which I have that component form right there.
Two.
No.
Oh, root 10.
Okay. Good with that?
Yes.
So what we just found was the lengths of each of these. So if you want to write them in, you can, but this is the square root of 10, this is the square root of 5, and this is the square root of 13. So to find this angle, we're going to do law of cosines. But you guys all rock law of cosines. Look, you got a 96 class average on the quiz, so everybody knows law of cosines.
Yeah,
We all
forgot.
What?
We forgot.
Jesus.
Okay,
All of size is better.
so since I want to know this angle, I start the law of cosines with its opposite side being squared. And that's equal to the two sides that include the angle squared. So u and v, their sums, minus 2 times the length of those sides that's included, times the cosine of theta, and that's what we're trying to find. Okay, so obviously this is 10. So remember how you have to do this. You can add these together, but you cannot subtract off this because it has a variable attached to it.
Yep.
All right, so that evaluated is 18. This is 130 cosine theta.
Dang.
How do you get 130 out of that?
Magic.
This times this, the radicals will cancel out, so you do 2 times 13 times 5. Is that not 130?
It probably is. Yeah, it is.
Yeah.
Yeah. Wait, so the radicals cancel out?
If you do 13 times 5 first,
I thought you had to multiply underneath the radical. And then it'd be something, whatever 13 times 5 is.
No, I think you're thinking of if you have like,
We got a minute.
okay.
Mr. G
Yeah.
pretty.
I don't know.
No, why does that work though?
I don't think
I
it
thought that you
does.
had to
Like
multiply
minus
underneath
two,
the radical.
Like the square root of?
Yeah.
I don't think that works.
It's minus 2.
Oh, but I times a 2 in there, didn't I?
Yeah.
Well, what is 13 times 5?
60.
So we're thinking it's 2.
It's gotta be 2 to 65, doesn't it?
Yes.
Because
Yeah, I think you're right actually.
because you're not squaring the radicals.
Yeah.
But I got the right answer
Sure.
for the angle. Yeah.
Oh well.
Okay, let's start this and revisit. I see what you guys are saying. Because if you have like the square root of 2 times the square root of 2, that's the square root of 4, which is 2.
Yeah. And if you have like square root of 3, square root of 4, that's square root of 6.
Okay, pause there. We'll
I need to
revisit.
start
I'll have to make sure
writing bigger.
I did my algebra right.
Did Mr. Riley teach us this?
Yeah.
Although
I bet
does
Mr.
know.
Riley